right, welcome again. This is the last part of this lecture. So far we talked about the design equation and how to find out the density of the gas. So to find out the density of the gas, we have to up this equation. It's equal to 2.5 open bracket specific gas for the gas multiply pressure over temperature and multiply the compressibility factor. Usually, such information are given in the problem. For example, here the temperature is given, the pressure is given. However, you have to convert that, as mentioned earlier, to Rankel and this to PSI absolute, and the compressibility factor is also given. So we can find directly the density of the gas. So it's equal to 0.67, which is the specific draft of the gas, multiply 1015, this is the absolute pressure of the gas stream, over 560, which is the temperature, 560 Fahrenheit, multiplied the compressibility factor, which is already given. Multiply 2.7, and finally we can calculate the gas density. The density of the liquid, which is the glycol, definitely the glycol is given, so don't worry about that. The CD is also given, which is 0.852. So now we can apply this equation to find out the diameter of the column, this side diameter. So this d square equal to 5040, which is a constant, multiplied by 560, which is the temperature on the Rankel, multiply 0.865, which is the compressibility factor, which is given, multiply 98, which is the flow rate of the natural gas, okay, is given here, 98 million standard cubic feet a day. All right. So over 1015, which is the pressure of the gas stream, here we convert it to absolute pressure. It's still PSI, multiply open bracket 3.72, which is the density of the gas. We just got calculated from this equation, and over 70, which is the density of the liquid, which is the glycol, minus the density of the natural gas again. Here we have we need the for example, the CD for the contactor, which is 0.852, which is given, okay, and we also need the DM. It's also given in this problem. For example, DM here, we say it's the range between 120 to 150. Okay, so don't worry, it's already will be given. Okay, so here is given is 125. Okay, and again, not forget that the power of this tail is 0.5. Okay, so the final calculated diameter is equal to 68.2 inch. We could use 72 inside diameter for the contactor as a standard. Okay, so here we found the inside diameter of the absorber tower. As you can see, it's a very easy procedure. Almost informations are given. Okay, for example, the compressibility factor, the DM, the CD. You just need to find out the density of the gas, and it's very easy and simple equation to find out the density of the gas. And finally, found the inside diameter. Okay, now I need to determine the glycol circulation rate. As I mentioned earlier, it's a very important factor in the dehydration process. Because the glycol dehydration circulation rate is very important and contribute in this dehydration process. So first of all, I need to find WI, which is the initial water vapor content. Okay, so here is 63 pounds per million centimeter cubic feet. Okay, the outlet of this will be given. Don't worry. And the WO, which is the desired water content after dehydration, is 7 pounds per million centimeter cubic feet of the gas. Okay, so here I can simply find delta W, which is WI minus W naught, so 63 minus 7. And delta W, I need to find out this ratio as well. Delta W over WI, which is 56 over 63. Okay, so this is 56. Okay, delta W over 63, which is W sub I. Okay. Here, if you remember, we talked about that. Here, for example, W is the water content of the inlet gas, delta W is desired outlet temperature. Okay, we mentioned the delta W over WI with circulation ratio. Okay, so after that, I can. Sorry. After that, I can find out the circulation rate of this dehydration process by adopting a two number of states, 8 actual trays, and for the glycol purity that given already in the problem is 98.5% from figure triple star. So this figure that I mentioned, figure triple star, is the fraction of the water removed by various TEG circulation rates that adopt 2 theoretical trays or 8 actual trays. So here we need delta W over WI that we already calculated, okay? And the given TEG rising glycol purity is 98.5. So here, for example, I need to cross this curve, okay, the second one. Let's say the second one from the bottom, the second one, okay? And then to find out the circulation rate here, okay? So let's check that. So the delta W over WI is 0.889. 889. So 889, yeah. Let's check that. Yeah, 889. So it's approximately here. All right. So it's approach from 3, but it's not 3. Let's find out the final result. The final result is 2.8 gallon of the triethylene glycol per pound of the water. Here, assume that you use 3 gallon per pound for the design. Okay, so no problem. You can use 2.8 or use 3. Okay, let's say it's been approximated to 3. Okay, 3 gallon per pound multiply 56 pound per million centimeter cubic feet, which is the delta W. Okay, multiply 98 million centimeter cubic feet of gas. This is the flow rate of the gas, and here we need to convert the time as well. Okay, so it's very easy. Finally, we can get the final result, which is the circulation rate of the triethylene glycol, which is 11.4 gallon per minute. Gallon per minute. Okay. So it's very easy procedure to find out the final result or the saturation rate of the glycol in the gallon per minute. Okay. Finally, designing the still column, we can also adopt an equation to find out the diameter. So here we need the dm, which is 125 micron. This is given. Temperature 300 Fahrenheit or 760 Reinkel is also given. The pressure is 1 psi gauge. The compressibility factor is 1. Okay, and the flow rate is 0.16 million standard cubic feet. It is also given. So here we need again to find out the density of the gas. So by adopting the same equation that I mentioned earlier, so you can find out the density of the gas. So here we need the specific gravity. We need let's see or revise the equation. So we go to this equation. So 2.5 multiply S multiply Q, which is the pressure, over temperature and the compressibility factor. So here we got the pressure in the PSI gauge. We need again to convert it to PSI absolute, and we already got the temperature. We convert it to Reinkel, and we have the compressive factor, which is 1. Okay, so the final result will be 0.35 pound over cubic feet. The density for the liquid is given. Don't worry about that. The CD is given, which is 40.2. And finally, I can find D. Okay, so D square equal to 5040, 760 multiply 1, which is a compressibility factor, and multiply 0.60 over 60, multiply open bracket 0.035, which is the density of the gas, over the density of liquid minus the density of the gas, multiply 14.2 over dm, which is 125. Not forget that this dm to the power 0.5, and finally you can find the inside diameter for the circle, 17.5 inches. Thank you very much for your listening. This is the end of the hydration lecture. Natural gas hydration lecture.